So, welcome to the lectures on Introduction to Statistical Hypothesis Testing. In the previous lecture, we learnt somewhat in detail the basics of hypothesis testing, the terminology, and more importantly the interpretations of the statistical terms and the quantities that we encounter in hypothesis testing, namely type 1 error, type 2 error, significance level and so on. What we are going to do in this and the next lecture is essentially learn how to set up the hypothesis test and run the test using all the theory that we have learnt earlier and the procedure for hypothesis testing that we learnt in the previous lecture. In this lecture particularly, we will look at the tests on mean alone, because there are a variety of situations associated with mean testing compared to that of variance and proportions. This is an exclusive lecture on the testing of means. To be more specific, what we are going to look at is so called one sample, meaning one population Z test. Again, here Z test means that we are going to look at either large sample size or data coming from a Gaussian population, or and then the T test, which will be concerned with testing of a mean of a single population, but with unknown variance. In the Z test, the variance is also known, that is important, but the Z test can also be come into play when the variance is known, unknown, but you have a large sample size. The T test comes into picture when you have small sample size and the variance being unknown and the data comes from a Gaussian population. Then we have the two sample tests, that meaning we are going to look at two populations and compare the means, where you have again unknown variance, the equal variance and the unequal variances, followed by the pair test. If you recall, the pair test corresponds to the test for situations where you have a before after type situations, either after a treatment or after a program that the individuals go through before and after. You want to check the effectiveness of the program and so on. And importantly, we will also learn how to conduct this hypothesis test in R in this lecture. So, let us begin with the so called one sample Z test for mean. So, the parameter that we are testing is mean of a single population. Assumptions, of course, I will not state this repeatedly. It is assumed implicitly that the observations are drawn randomly, which means the sample constitutes a random sample. Apart from that, we assume that the population standard deviation is known and that we have a large sample size. Of course, this large sample size is not a required assumption if the sample is being drawn from a Gaussian population. We have repeatedly learned this. Again, we have this standard, this is a generic statement of null hypothesis and alternate hypothesis. The actual alternate hypothesis depends on the problem in hand. And then as usual, we have learned many a times that the test statistic for this is a standardized sample mean, which follows a standardized Gaussian distribution. And the critical region once again depends on the alternate hypothesis and the significance level that we specify. If you recall from the previous lecture, in order to compute the critical value for a given alpha, we can use Q norm in R. Alright, so let us look at an example here. Again, this is our familiar example of the propellant burning rate from the book by Montgomery et al. The goal here is to test whether the average propellant burning rate is of the population is 50 centimeters per second. For this, we draw a random sample of size 25 and estimate the sample mean to be 51.3 centimeters per second, and the standard deviation is known, let us say it is known to be 2 centimeters per second. Clearly, we have discussed this many times before. The alternate hypothesis is that the true population is not equal to the postulated value, which is 50 centimeters per second. Compute the Z statistic, which is x bar minus mu naught by sigma or root n, and it works out to be 3.25. And then the critical value, as we have computed in the previous lecture, is 1.96. This is a standard thing for a Gaussian distribution at alpha 0.05. For a two tail test, the critical value is Z C is 1.96, it is nothing but Z alpha by 2. Since the observed statistic is lying to the right of the critical value, we reject the null hypothesis at this significance level. Once again, you can use the p value method also to determine the outcome of this hypothesis test. In fact, this is nothing but a recap of what we did in the previous lecture, right. Therefore, we will not discuss much. Let us move on to the second example or the second scenario, where we are looking at testing mean of a single population with unknown variance and assume that we have small samples. If we have large samples, then we can actually go back to the Z test itself. So, assumption is that the population standard deviation is unknown and that we have a small sample size. The null as usual is as before, and the alternate could be one of the triplet. Test statistic, we have now a t statistic in place of Z statistic, which is more or less like the Z statistic, but with the standard deviation, theoretical standard deviation replaced by the estimated one denoted by S, and this test statistic follows a t distribution with n minus 1 degrees of freedom. We have already discussed, you may refer to previous lectures, why this test statistic has follows a t distribution, particularly with n minus 1 degrees of freedom. And a critical region is as usual, we do not have to elaborate much on it. Now, if when you want to conduct these kinds of tests in R, you can use the built in command from the statistics package, stats package in R, which is the t dot test routine with the conf dot level. This conf dot level is known as is nothing but your significance level. Sometimes it is called the confidence level or sometimes and other times it is called significance level, but remember that it is not, they are one and the same. So, you specify at whatever value of alpha you want to work with. Let us look at an example here. So, training method A, which we have discussed in the motivation lecture when we are talking of comparison of means. So, training method A is considered effective if the mean score is at least 75 on a test that is conducted after the training session. So, the null here is that the mean score for the trainee is at least 75, right, and given of course some data. Let us talk about the alternate hypothesis. Alternate hypothesis is it is not. So, together they span the entire set of possibilities. So, what we are searching for here is evidence to reject this null hypothesis that the training method is effective. Of course, you can also have another kind of situation depending on the null. Here the null is that the mean score is at least 75. If you think that the default, that means in the absence of data, if you are willing to accept that the method is effective, this is a null. But if you say no, in the absence of data, I would say that the method A is not effective, that is what is your null, then you would say that the null is mean score is at most 75, and then the alternate becomes the complement of it. So, here we are assuming that the default by default will accept this training method. So, let us essentially we are giving a benefit of doubt to the person who has come up with this training method, but that need not be. So, a sample of 10 individuals are drawn at random and the average scores turns out to be 70 with a standard deviation estimated to be 3.366. It fits in perfectly with the scenario of one sample t test, and we compute the t statistic, turns out to be minus 3.91, and this is a one sided test. Therefore, we seek the corresponding critical value from the t distribution with 9 degrees of freedom, because n is 10 here, and that turns out to be minus 1.833, and since the observed statistic is more extreme than what is tolerable, we reject the null hypothesis at this alpha. I have this data set loaded, and in fact we will upload this in R. This example is from the book by Ognaike. Let me show you how to load the data set and run the t test on your machine. Okay, so, if you want to fire up R on your laptop, get ready, pause the video. All right. So, let us see here, if you will be supplied this file called methods.rdata, and use the load command to load it, and you will see in the environment a variable called xmeth loaded. It has two columns in it, scores for scores for training method A and training method B, because this is an example that we will visit again later on when we compare means. We are interested at this moment in the first column. In fact, we can actually it is a small size. So, we can look at the first column, you have 10 observations, that is the data. Although the data is printed as a row, it is still a column data, please remember that. In fact, we can ask for a summary of, these are called summary statistics, it gives you mean, median, and also min and max, which gives you an idea of the range. You can also estimate now the standard deviation, which is what I have reported for you in the example. Let us also plot, it is, as I always say, it is a good habit to visualize your data, and let us do that. This is how it looks like. Maybe it is better to plot it as a line overlaid on marks. So, we can ask for overlaid plot. So, you can see here, this is how the data looks like for the method A. Now, we can also draw a box plot, play around with it. Let us get to the point here. I can run the t dot test. Look up the help on t dot test before you do this. There are a number of options. You can bring up the help on t dot test. You can see that this t dot test is suited for both one sample and two samples, single population and two populations. And then there is an option to specify the alternative as two sided or less and greater, means lower or upper tail test. Then you specify the confidence dot level, let me maximize the screen for you, confidence dot level, which is nothing but your significance level. Then later on we will have an option called var dot equal, that is for comparison of means of two populations with variances unknown, do we assume that the variances of two populations are equal or unequal? By default it says it is false, that means it assumes that the variabilities are different, and then there are a few other things, but we will not worry about that, all right. So, what is the default version of t dot test? That it assumes it is a one sample t test, and also there is a mu equals 0, forgot to mention that. That mu is nothing but your postulated value, and in this example the postulated value is 75. We need to specify that, otherwise the default value is 0. So, let us do that. We will ask for t dot test, the first variable method A, and we specify mu to be 75, and conf dot level by default is 0.05, but let us be sure to specify that, right. But alternative, that is very important. Our alternative here is that the mu is less than 75. So, we say alternative is less, and we run the test. So, here is what we would get here as t dot test. Let me actually make a small change here. It looks like this t dot test has been taken from another package that I have loaded. Let me make sure that, so this is what happens in R. When you run a certain command, there may be a routine with a similar name in another package, and what I am trying to show you here is the t dot test that comes from the stats package. There is a t dot test that also comes with the env stats package that we will use in the later lecture, and the t dot test that I just ran is from the env stats package. So, let us make sure that I show you the t dot test from the stats package, all right. So, when we do that, let me actually, or the other thing is to just unload the package nstats. Yeah. So, this is the output that you would see when you run the t dot test package. Here I have forcefully unloaded the other package which had a conflicting t dot test. just to make things simple, and this is the output that you will see if you are using the T dot test from the stats package. If you want to go back to the N stats package and use, this is the kind of output that you would see that from the N stats package. In fact, it is very nice, the output is nicely formatted compared to the output that you see with the stats package. In fact, let us look at this, because later on you will have to install the ENV stats package and load that package as well. So, we might as well understand what this T dot test looks like. The output is the same, it is just the way the output is presented is making a difference, and you have this output formatted in a very nice manner. So, what do you have here? The null hypothesis is mean 75, conforms with what we have given. Alternative hypothesis again is what we want, and it has conducted a one sample t test. The estimated parameter is 70, sample mean, and then you have the test statistic working out to be minus 4.69. All right. So, the actual test statistic is minus 4.69. This is why it is important to run the data for yourself. Of course, in this example there was an error, but I will leave it at that. Maybe when I post the notes I will correct in the slides. We have minus 4.69, we will add a note to the slide there, I will not correct the value. All right. So, the degrees of freedom is 9 and the p value is reported. So, the p value is way low, I mean it is quite low, it does not matter how low it is, it is much lower than alpha. What does it tell us? It means that the test statistic has fallen to a more extreme value than tolerable, therefore, this null hypothesis has to be rejected. And also what you see here is confidence interval, which I will briefly talk about later on and more so in detail in a lecture later beyond the next lecture. All right. So, the test does not tell you whether you should reject or not, that is what is important to know. It reports the p values, it reports the test statistic, and you can of course the critical value you have to calculate from the Q norm, but since you know the p value, you might as well avoid calculation of the critical value and straight away say that the null hypothesis is rejected. For your own convenience, I have reported the critical value here, whereas the T dot test gives you the p value. Either way, the null hypothesis is rejected. All right. Now, let us look at the 2 sample Z test for mean. Again, what we mean by Z test is that the population standard deviations are known, the parameters of interest are still mean. Again, if you look at the problem statement, fairly generic, the null that we want to test is the difference between the means of the populations is a postulated value delta naught, and the alternate hypothesis one of the 3 possibilities. Test statistic we have seen earlier, the standardized sample difference in sample means follows a standard Gaussian distribution, and the critical regions are as before. Here there is no built in command per se for Z test, because it is one of the simplest things that you can do by yourself. So, there is no routine, but you can write a small function or a script to do that for you. And let us go through this example. The goal here in this example is to test that battery A has longer lifetime than battery B. So, what is the null here? Battery B existed before, and someone has said that battery A that I manufactured is better. So, the null is that battery A is as good as battery B, because battery A has been introduced newly. So, and the alternate hypothesis is that battery A is better than battery B. Essentially what we want to test goes and sits in the alternate hypothesis in some sense, but what we want to test also depends on what is null. It is better to state both. We have randomly drawn 40 specimens from both these populations, sample means have been calculated, and the standard deviations are known, and the critical value, once you put in all this data through this generic procedure, the delta naught, what is delta naught here in this case? It is very easy to guess, it is 0. So, plug in the values of delta naught, x1 bar, x2 bar, sigma 1, sigma 2 and n1 and n2 and get the value of z, work it out, it turns out to be 1.38 and which falls within the acceptable region. Why? Because alpha is 0.05 and we know that this z statistic follows a standard Gaussian. Therefore, the situation that we have here is that the critical value, it is a one sided test, remember it is an upper tail test. So, z alpha is going to be 1.65 roughly and 1.38 is less extreme than what I am willing to tolerate and therefore, I fail to reject the null hypothesis. In other words, that what does it mean? That the null which is battery A is as good as battery B holds. There is not enough evidence to believe that battery A has a longer lifetime than battery B. That is the outcome of this result of this hypothesis test. Alright. So, let us move on to the case where the standard deviations are unknown. We know there are two possibilities, variances are equal, but unknown and the other possibility is variances are unequal and unknown of course. And of course, we assume also that the populations are Gaussian, then only we can use this result strictly speaking, otherwise it is going to be only an approximation. The hypothesis is the same as in the two sample z test that we went through. Test statistic is the is different now based on the fact that we are going to use pooled variance also, but even otherwise, even if the variances were unknown, the test statistic would be still this t statistic which follows a t distribution with n1 plus n2 minus 2 degrees of freedom. Again, maybe as we go through each of the scenarios, you may want to keep the lectures on sampling distribution by your side to see at what point and to go to the point where we discuss the sampling distribution of each of the statistics. And the pooled variance is calculated using the given formula. The critical regions are as usual based on the t distribution and a pre-specified value of alpha. Here we use again the t dot test with var dot equal being set to true, that is the case. So, let us look at an example now. We are going to compare training methods. Earlier we tested the effectiveness of method A, now method B has been introduced and we want to test if this method B is more effective than method A. So, the default is method B is as good as method A, right, like we did in the battery case. Of course, here B and A are reversed, there B existed, A was introduced, now A exists and B is being introduced and being claimed as more effective. So, again we draw random samples from both these populations of size 10 and the data is also already preloaded for us. We will go back, we will go to R and test this, but let us see what our numbers tell us. The numbers are reported. The alternate hypothesis is clearly mu A minus mu B is less than 0 and the test statistic turns out to be minus 1.989 when you plug in all the values here. That is what the t dot test routine essentially does for you, and the critical value is minus 1.73. Since minus 1.989 is more extreme than what I am tolerating, remember this is a lower tail test and my observed statistic falls to the left of the critical value and therefore, I reject the null hypothesis, which means indeed method B is more effective than method A. Let us look at this in R, how to do it in R. Let us get back to R here and now perform the t dot test in the stats package, and we say here x equals x method 1, that is our first column, and y is x method second column, and we want to set var dot equal to true, and the rest of course mu is 0 by default, we do not have to specify. The rest of the defaults hold in place. So, one thing that we will have to do is alternative should be less, so that the critical value or the p value is calculated correctly, that is very important, right. That is what we had. If you look at the alternate, it is a lower tail test and that is what we are doing, all right. So, this is the outcome. We could of course use the env stats package, see how the thing comes out to be. But as I said earlier, the output is the same, it's just the formatting or the way it is printed on the screen that makes a difference. All right. So, the test statistic works out to be minus 1.989 as I had reported in the slide for you, and the degrees of freedom is 18 because it is n 1 plus n 2 minus 2, 20 minus 2. The p value is given and the p value is less than the specified value of significance level, which is 0.05. That means, what I have here is more extreme than what I am willing to tolerate. What I am willing to tolerate is p value should have been 0.05 in other words, and alternative hypo is also reported for you. And once again this t dot test reports a confidence interval. As I said, we will come to that part of the output a bit later. That is it. So, this is how you implement things in R. Now, let us get back to and move on to the next kind of situation, where we have unequal variances. The story is more or less similar for the as in the equal variances case, except that the degrees of freedom calculation is a lot more involved and the way we estimate the variances are different. Earlier we used a pooled estimate, obviously because we assume the population variances to be equal, we exploited that fact and used not 10 and from A and 10 from B, we pooled it together to estimate the variance. Here we cannot afford to do that, the variances are different, therefore, we have to use the respective random samples to estimate the standard deviations. And rest of the story is the same, except that now you use variance dot equals false in the t dot test, which is the default. Now, the example is different here. It is desired to test if two reactors A and B have the same yield, all right. And from data we have n1 equals 50 and n2 equals 50. We have the same sample size, but of course, the sample means are going to be different, the standard deviations are different. Because the goal is to test if two reactors A and B have the same yield, the alternate is naturally that they are not. One could have more or less than the other. And for this data, we have here the t test statistic worked out as reported here 6.92. The degrees of freedom after all these calculations works out to be 73. This is much more complicated than in the equal variance case. Now, I report the confidence interval for you, which is 2.169 and 3.924, and we know that we can use here either the critical value, you can go and use the Q norm for example, sorry Qt for this example at alpha equals 0.05. In fact, because it is a two-sided test, we should be looking at Qt with a Q norm of 1 minus alpha by 2, that is how Qt works with 73 degrees of freedom. So, we can actually go and check in R what are the critical values here. Let us ask what is the critical value for 0.975 and degrees of freedom 73. It is fairly high, it should be more or less like a Gaussian thing, and you see that it is almost close to what you would see with a Gaussian value, right. Now, there is this yield data that I have for you. You can also do it in R. So, whatever we did in the slides, we can do it in R. Let me clear the screen so that it is not jumbled up. In any case, going back to before we jump into the R session, the critical value is 1.96 and the observed statistic is 6.92. It is quite extreme. In fact, it is does not matter, as I said, how far it is to the right. It is to the right of the critical value, which is roughly about 1.9394, and therefore, we reject the null hypothesis. What this means is that indeed these two reactors have different yields, all right. So, let us actually see if we can run this on the in R on the data that we have, all right. So, this actually again loads a variable called x yield. We will make this data available to you. This example is from the book by Ognaike. And what we want to run is the t dot test. In fact, it may be a good idea to plot the yield data both A of B and A. So, we can here plot the first column. So, this is the one that you see for A, and we could also plot here lines or maybe points for B. And here change the color, let us say to red, so that B is in red. So, you can see here that B is in red. Maybe we can also do a lines here along with the points. There you go. So, of course, the problem with this is the problem with R, that it does not adjust the axis automatically. We could have plotted B first and then plotted A. Anyway, you may want to actually plot A and B individually. There are ways of overlaying this. I am just doing a very preliminary thing here, just to get a feel of the variability that you are seeing in this data, how different things are with respect to variability and averages and so on. You could do a box plot and so on. But let us focus on the task in hand, which is to run the t dot test, and here we have x yield the first column and then yield the second column, and variance dot equal false, mu is 0 and its alternative is two sided. So, all the defaults hold and we do this. So, let us see what we get here. Degrees of freedom is roughly 73, I mean it is 73 point something, but degrees of freedom has to be an integer, because it has got to do with the number of sources of variability, and that number is an integer. However, with the expression that we had for the calculation of degrees of freedom, you are not guaranteed to get an integer. Therefore, in practice we round it off to the lowest value. So, that is the 73. To be conservative, we round it off to the lowest one, not to the higher one. And then the p value is reported here, extremely small. What does this tell us? It is very low, does not matter how low, it is much lower than alpha by 2, alpha, and therefore, the null hypothesis must go. The confidence interval that I have reported here is given, is also displayed here. Now, let us understand very quickly what is confidence interval here, the technical details of which will be discussed in a later lecture. The confidence interval offers another way of conducting the hypothesis test. It is essentially the region in which we believe the true value is residing, all right. But again, that is not with 100% confidence, because the alpha here is 0.05. We say that this is a 95% confidence interval. That means there are 95% chances that the truth is contained in this interval. It might as well be outside this interval. You may end up with a realization that will not give you an estimate which is consistent with this confidence region. But let me put it the other way, that there is a 5% chance that the truth is outside this interval. That is a way of understanding. We will illustrate those points later on in the technical discussion. Right now, let us quickly understand how to use this confidence region. If the postulated truth is contained in the confidence region, then the null hypothesis will not be rejected, may not be rejected. Now, the postulated value for the difference in means is 0, and 0 is not contained in this confidence region. That means, most likely the truth is, the fact is the truth is not 0. There is a 5% chance, that is a type 1 error, there is a 5% chance that truth is 0, and I am not able to capture that in this confidence interval. But I am kind of 95% sure that the truth is in this region. Based on that assertion, we reject the null hypothesis. Now, this is for a two-sided test. For a one-sided test, the confidence interval, if you recall, looked different. There was, for example, for a lower tail test, it was anywhere between minus infinity and some value, or for an upper tail test it was some value, the confidence region was some finite value and infinity. There also we can conduct hypothesis test using confidence region. The principle is the same, the postulated null value should be in the confidence region. If I cannot find it in the confidence region, that means it is not one of the possible truths, then we reject the null hypothesis, and that is the case in this example as well. All right. So, that is the scenario here, you can see the postulated value is not. But suppose we wish to test, now that we have realized that A and B are reactors with different yields, and now suppose I wish to test that the difference now, that means I know for sure A and B are different. Now, I want to test whether the yield of A is greater than yield of B by 2%, let us say. Then what would be the result? Since you have the data, now since you know the alternate hypothesis, you can actually conduct the T dot test or T test and let us know the answer, all right, on the forum, or you can send an email privately. It is just a homework problem. You know what now the mu should be set to. Do not forget to set the mu in T dot test to what value? Well, guess what that value is, and then run the T dot test accordingly with the right alternative, you will get the result. You will also get the confidence interval, see if you can use both the p value and the confidence interval to arrive at the answer. Very good. Now, the last in discussion is the paired test. As you remember, even in the case of sampling distributions of mean, this was the last scenario where we are still testing for differences in means, but with populations that are not independent. And we had said at that time there are many scenarios that many situations which correspond to this scenario. So, here the samples that I am drawing form an ordered pair. That means, it is the same individual which goes through 2 different programs, or maybe an object that is before, let us say I am testing a detergent for its cleanliness index or effectiveness in terms of cleaning. I have a cloth, dirt levels, and then I put it through the cleaning agent or the detergent, and then comes out I have another cleanliness index. That also is a scenario, falls into this scenario, and so on. So, the main point is that the variables in the pair are not independent, unlike in all the previous comparison of means cases. The null hypothesis is now that the difference is a postulated value. Here we use delta, we do not say mu 1 minus mu 2, but we simply test for the difference straight away, delta equals delta naught, and the alternate hypothesis is one of the 3 possibilities. Now, the test statistic is the T, standardized T statistic, delta naught is a postulated value, SD is the estimated standard deviation from the given data, and we have gone through all of this, and the critical region is as usual. Now, in the T dot test, as I said, there are several options, including that for paired, which is usually set to false. Now, we set it to true. And here we have an example of a weight loss program, where we wish to test if the weight loss program has caused any difference in the weight. Of course, the natural and the intuitive thing is to check if the weight has decreased, but it is possible that the program has also caused a harm. Many a times people go through some weight loss programs and after a while immediately gain weight. So, we want to see if also that has happened, and therefore, initially we will ask if there is a difference between the weights before and after. And once again here I have the data for you that you can play around with in R. There are 20 points, the calculated difference and the standard deviation are reported here. Alternative is delta is not equal to 0, because we only want to see if there is a difference, and the confidence interval is reported here. Based on the guideline that I have given you earlier, the postulated value 0 is not within the confidence interval, this 95% confidence interval, and therefore, we reject the null hypothesis. What does it mean? That the weight loss program has indeed caused a difference in the weight. We have not tested, however, whether it has decreased the weight or increased the weight. That you can do, but let me since you have the data, right. So, we will come to that. Let us actually see how we do this in the R. So, let me load the data here. So, the data is contained in weight loss dot R data, we will provide this data for you, and now we have here XWT as the variable, and once again we run the T dot test. XWT contains 2 columns, but anyway before doing that let us actually plot XWT. Oops, sorry, this is one against the other. So, let us plot. All right. So, this is the weight before the weight loss program of this 20 individuals, and now we can actually draw so you can see here, in fact we can now perhaps join them by lines as well like we did in the previous case. You can see they look pretty similar, they better be, because they are the same individuals and their weights before and after cannot be, I mean they can be different, but they should, if it has been effective and for an individual, you expect that it should be effective for a lot of other individuals as well. But the point, there are 2 points to observe. One, that there is a strong correlation between the weights, which means they are not independent. Remember we talked about independence and correlation. In fact, you can compute the correlation coefficient for this and also run a test of correlation whether it is 0 or not. And secondly, you can see because of the heavy correlation, the variability within the population is much higher than the variability across populations. That means, the within group variability is much larger than across group variability. That calls for a pair test. If it is not the case, then you can actually treat it as different. All right. So, let us look at this here. I have T dot test. Let us quickly do this here, and we set paired equals true, and the rest of the defaults are the same. Mu is 0, the significance level is 0.05, it is a 2-sided test, therefore, I do not have to be worry about anything else, and that is it. So, here we have the values. Once again you see that the numbers displayed here tally with what we had, especially the t statistic value and the confidence region. You can also see the p value being reported as usual, which I have not reported in the slide. It is low than alpha, right. I do not want to say it is much low, it is lower than alpha, and therefore, the null hypothesis is rejected. Now, what I would like you to do as a homework is try and run a 2 sample t test, that means treat this populations as independent and see what the result comes out to be. I leave that as a matter of surprise for you. What happens when you turn the paired option off, and maybe you can say the variability is the same, variance dot equal equals maybe true, and try to run the test, and variance dot equals being false, try to run the test and see if you had inadvertently treated these 2 populations as being different, whether the result is contradictory to what you get from the paired test or in line with what you see from the paired test. And the other thing that you could do is also, once you are convinced that the paired test is a better way of doing it, go and run now with a different alternate hypothesis, that after the weight loss program the weights are lower than before, right. So, you have to frame the alternate hypothesis, but still it will be a paired test and see if the null hypothesis that they are equal is rejected in favor of the alternate hypothesis that weight after the loss program is the lower than weight before the weight loss program, all right. So, make sure that you work out things in R, we will have all the data sets available for you, play around with them, plot, do go through the summary statistics, draw the box plots, put everything together in perspective, and then hopefully you will enjoy the hypothesis testing a lot more than just simply running the data through this T dot test. In the next lecture, we will look at testing for variances and proportions. All right then, until then, have a joyous R session. Bye for now.